Today we're going to be talking about Fermat's little theorem. So in the last video we went over fast modular exponentiation, where we computed large numbers like this. And if you recall, there was a better way to compute this than just multiplying it out like this. In our examples last time we would do something like 3 squared to the 10th, which is equivalent to 3 to the 20th, would end up giving 9 to the 10th, and 9 would be congruent to 2 in mod 7. So that would make this 2 to the 10. Okay. And we would go through that problem and we keep doing reducing and moving around exponents and reducing and moving around exponents until we eventually got to a number was within the bounds of of this or whatever m would have been in that case. Okay. So today we're going to be going over certain cases where you can use Fermat's little theorem to actually speed up this process and get an answer even quicker. Okay, so for Fermat's little theorem, what it says is that um if we're in mod P, which is a prime number, and A is not divisible by P, so this does not equal an integer, then this statement here is true. So let's take for example, if we had 3, let's do the 6 is congruent to 1 in mod 7. So since 3 is not divisible by 7, then that means that 6, which is p minus 1, which becomes 6, is congruent to 1. So when say like we had a problem and this was like 10, we could then just hypothetically, we could rewrite this as 1 to the 10th, which would just be 1. Okay, so we're going to be going over an example problem and we're going to be using this theorem to help us solve that. Um, whenever you're in the mod of a prime number, try and find that first, and then see if a divided by p is an integer or not. If it's not divisible, then use Fermat's little theorem, and that will speed up the process even more than we would with fast modular exponentiation. Okay, let's do this example right here. We have 13 to the 100th and mod 9. So remember, we could use fast modular exponentiation here, or could we use Fermat's little theorem? I want you to try and think about if you can actually solve this problem with Fermat's little theorem or not, and then we'll move on. Okay, so in this problem, recall that Fermat's little theorem requires that P is prime and that um, A does not divide P. We'll say K where K is in the set of integers. Okay, so these are our criteria for being able to use Fermat's little theorem. Okay, so let's start off with is P prime. So we have um okay, so using this definition, what we can see here is that mod 9 would be our P. So 9 would be our P. Is 9 prime? Now, hopefully you said no, because if we take 9 divided by 3, that equals 3. And we know that a prime number are only divisible by themselves and 1. So 7 is divisible by 1 and 7. And that's it. 9 is not prime, so we cannot use Fermat's little theorem here, and therefore we'd have to go about solving this in a different way. We're not going to write out or compute this entire problem. I just wanted to show you that sometimes you will not always be able to use Fermat's little theorem. So let's move on to the next example problem. Okay, let's do this example problem. The 3 to 20th and mod 7. I want you to try this on your own first and then come back if you have any issues or to check your answer. Okay, for step one, let's see if we can actually use Fermat's here. So is 7 prime? Yes, it is, because 7 is divisible by only 1 and itself. So that criteria meets. Now, um, is uh is A divisible by P? So A divided by P would be 3 divided by 7. This does not equal K, where K is an integer. So it meets the criteria for Fermat's little theorem. So now let's actually use Fermat's little theorem. Or let's go over the definition for a section. So remember, we need A to the P minus 1 is congruent to 1 in mod P. So in this case, we need A to the 6th, or 3 to the 6th. So I guess what we could start off with is like, we could end up doing like this until we add up, um, until there, but I think we can do this a little better. So remember that exponents multiply. When you have a number to an exponent, those multiply together. So 6 times 3 is 18. So that'll get us relatively close there if we do that. And then we're just missing 2 more 3s. So just do this. Okay, now recall this is 1. So we can reduce that there. Here, let me explain this for a section. Okay, so this will actually is equal to 3 to the 18 times 3 to the 2, which is equal to 3 to the 20th. Because these multiply here, and then these add there, which gives us the equivalence of 3 to the 20. So that's why I did that. Um, okay, so now let's move on. Actually, let's run through this again. So this will actually give us 1 to the 3 times 3 to the 2. 1 to the 3 ends up just being 1, multiplied by 3 to the 2, which is 9. So this equals 9 here. I don't know why I can't write that right. Okay, and we're in mod 7. So what is 9 congruent to in mod 7? It's 2. And we can look at this by taking 9 minus 7, we get 2. So yeah, that checks out. So our answer here is 3 to the 20th congruent to 2 in mod 7. And we just computed that using Fermat's little theorem to simplify this and make this problem easier. Okay, to do a quick recap, we just went over how to solve or compute these larger numbers using Fermat's little theorem and fast modular exponentiation. So to recap, we can use Fermat's little theorem when P is prime and and A is not divisible by P. So if P is not prime, we cannot use it. And then if A is divisible by P, then we also cannot use it. We need both these conditions to be true for us to be able to use Fermat's little theorem. So that's the first step, is check that those conditions are true before you use it. Two, rework these exponents to get to A minus B, because in this definition, it tells us that A minus B is congruent to 1. So getting to that somehow will make solving these problems easier. And that's actually like how we will literally use Fermat's little theorem to compute these larger numbers. So you need to be able to rework the exponents in some way to get to A minus B somewhere so that you can replace it with 1. And then step number 3 is just to compute it. So once you get to that 1, you should be able to be reduced enough to um, solve it within the next 2 steps or somewhere around those lines. You don't need to, like in the case before, we had 3 to the 6 was congruent to 1, but we had 3 to the 20 is what we need to compute. You could have done this, but like obviously this all just end up equaling 1. But a clean one line move that you can do here is, let me write that back again actually. This equals 3 to the 18th because these just add together. So instead of doing it that way, what you can do is you can just do 3 to the 6th to the 3rd power, because these will just multiply. So this ends up being 3 to the 18th anyways. Um, Whereas in this one, you would end up doing 1 times 1 times 1. You might want to write that out, you might not want to. It's more clarifying if you do. But in this case, then you can just show that 1 to the third equals 1. And so, try and use this property of exponential multiplying to your advantage because that'll also greatly help you. So that was Fermat's little theorem. Thank you for watching. I really appreciate it. Comment if you need a better explanation, different example problems, anything. I'm also doing online one-on-one tutoring, so if you're interested in that, check the email in my bio. And and thank you for watching. If you could like and subscribe, I'd really appreciate it. And have a good one.